How do you do, ladies and gentlemen, and boys and girls? I'm Julius Sumner Miller, and physics is my business. And our business today is the very special third law in Newton's three laws of motion. And to view it at least once in our lifetime in the Latin, I have it here. Lex 3. Actione contrariam semper et equalam esse reactionem. Now, if you didn't know any Latin at all, you'd see something in there about action and reaction. And indeed, that's what it sums up to be. Third law, to every action, there is always an equal and opposite or contrary reaction, or the mutual actions of any two bodies are always equal and oppositely directed. Now, a strange introduction to this law would be as follows. Consider me standing still and quiet on the earth, and I jump up in this manner. I ask, did you feel the earth recoil? And the answer is, it must be, it did indeed recoil, even though you may not have felt it. Why? Here is the earth, enormous mass. Here I am, a teeny-weensy creature of little mass. I push down on the floor with a force F, which acts on me and on the earth. And as before in the second law, my little mass, you detect, has an enormous acceleration. Up I go. But the earth, having an enormous mass, has a teeny-weensy acceleration, which you cannot detect. So, consider Newton's third law in a toy. Here is a little vehicle with some wheels, to which is fixed a rubber balloon, and I blow some air in the balloon. Now I'm going to let the air come out of a certain hole, orifice here. The air comes out this way, and what must the vehicle do? The vehicle must go the other way. Watch it. There it goes. And so I am reminded of a certain exercise that goes like this. Here is a rocket vehicle. We have some stuff in here in a state of combustion. The products of the combustion come out here, millions of little particles of stuff. Now, many people have the distorted notion that this stuff coming out here must push against the atmosphere in order for this to go. And I say that is utterly erroneous. This system, this vehicle, works better where there is nothing, because we want the little mass of stuff coming out there to come out with the greatest possible velocity and hence have the greatest rate of change of momentum, the product of m and v being momentum. Now, I'm going to go back to the two cars, because the case of the two cars, I said earlier, very important. Massive car, less massive car. I stretch the spring between them. One and the same force acts on both, and we witness an astonishing thing. Here is the massive car, here is the little car, less inertia, there is the spring. Now, what did we see? The same force acted on both. But you notice that the smaller one had the bigger acceleration, and the bigger one had the lesser acceleration, and therefore, in the same time of travel, and they would both travel the same time from time zero to the time of collision, clearly the smaller one has the higher velocity. So, writing the momentum of both cars, we would equate it as follows. The large car has a little velocity, the little car an enormous velocity, and these momenta are equal. Very important that you see that point, that the same force acts on both, the accelerations are inversely as the masses, and the momenta are equal. In another program, I will talk about their energies, and we will discover a very strange thing. Now, more on this conservation of momentum, which is essentially Newton's third law. Here I have a CO2 cartridge. Gas in here under enormous pressure. Here is a carriage in which I put it. I'll look around that end. And you will notice that there is a barrier on this end of the cartridge, of the carriage. Now what am I going to do? I am going to make a hole in this end of the cartridge. The gases come out this way. Oh, I erased that before. The gases come out this way, and they have a certain momentum, their mass and their velocity. The vehicle must go the other way. Watch it now. Watch. There it goes. There it goes. Miller's earthbound rocket. Now, a very important thing. It fled away. Fled away. Momentum, I'm sure. I would have asked a question had I had it in hand. Question. I would feel it to be very cold. Very cold. And I want to know, why is it cold? A second question. There could indeed be frost on it. And the question is, where cometh the frost? In the first question, we have a very powerful piece of physics. The gases coming out must do work. This costs energy. And I leave it there for further discussion in another program. Now, let's go to something still more dramatic. Again, conservation of linear momentum. Here is an array of steel spheres, highly elastic. Steel is highly elastic. By that I mean, when they are deformed, they recover. They lie in the lowest potential configuration. I take one up the plane, let it go, having given it some potential energy, and it collides with the system at rest, and watch what happens on the remote end. 1. Oh, that's terrific. Watch it. Look it. Nearly instantaneously. Indeed, I'm led to ask, how fast does the impulse get down there? Answer, with the same velocity as the velocity of sound in steel, which is about 15,000 feet per second. So if this were a foot long, oh, that's more likely a foot long, that's 9, 12 inches. Watch it. One 15,000th of a second. You notice, too, that the whole system experiences some motion. That's because they all wish to seek a lower potential plane. Now, 1 at collision mv. 1 goes away mv. Watch 2. 2 mv plus mv, 2 mv. Now let us disregard the intermediate or the other motions that we witness, because a discussion of this would divert me from my purpose here. All I wish to say is that whatever the momentum before the collision, so that is the momentum after. 1, 1. 2, 2. 3, oh, notice they are seeking a lower potential plane. The energy of a system runs downhill. 3, oh, that's pretty. Notice they are seeking a lower potential plane. 4, watch it now. Notice they are seeking a lower potential plane, just as my energy is running downhill now as I do this show. 4. 5 up. 5. And so we say, without question, the momentum before the collision is equal to the momentum after. Consider another classical demonstration of mine, which is easy to do and quite dramatic. Here is a steel pipe. This demonstration I will call virtual, V-I-R-T-U-A-L. There are some demonstrations that I do for real, and I call them real demonstrations. This one we will imagine, and imagination is a very necessary ingredient of this business. We will imagine a steel pipe closed up tightly on one end with a cap, mounted on wheels, and in this chamber I put some dry ice, solid CO2. Then with a wooden plug, I plug it up very firmly, and I let it stand here on the table in the hot air of the classroom or the TV studio, and what happens? The CO2 sublimes, goes into gas or vapor. The pressure builds up more and more. The pressure gets enormous inside. Something has to go. What goes? The cap, with an enormous velocity, enough indeed to kill a man. So if you should do this, I warn you, have some caution. And what happens to the vehicle? It goes the other way. Big mass, little velocity, little mass, large velocity. Conservation of linear momentum. Powerful business, powerful. Consider toys have a large role in my business because the physics of toys is an enchanting thing to engage in. Toys, I would have you understand, ladies and gentlemen and boys and girls, toys are intended for child's play, but the physics of them is hardly that. Here is a little propeller with some inclined blades, and I have mounted it in a chamber wherein resides a spring. So I am storing some wound up elastic energy in the spring, and I release it. I did that one prematurely. What happens? How is Newton's third law? How does it play a role here? Answer. The pitch blade engages the air, drives the air down with a momentum mv. The vehicle must go up. Watch it. There it is. Oh, that's a pretty thing. And then it's spinning as a top, about which I will speak in another program. So the question to be asked is, how does a bird fly? Here is a bird flying. Here is a bird. I'm probably viewed as a vulture. Bird. I can only fly if I push the air down, and that's why I go up. Now, when a bird soars, as they do ever so gracefully, that is quite another thing, again, to be considered subsequently. Or a balloon. Here's a balloon. Incidentally, I'm going to do a program on bubbles and the like, and I will raise the question of why is it hardest to blow up a balloon at the very beginning and easier to blow it up the bigger you get it. But anyway, I've put some air in there. Now you know if I let the air out here, momentum mv, momentum the other way. There it is, like that. And one last exploration. Hero's engine. Here is a little vehicle you can make out of a tin can. You put some tubes through it and bend the tubes at right angles to their lengths. Put some water in here. Boil the water. The steam, more exactly vapor, which becomes steam on condensation, the vapor comes out the orifices, and this turns around ever so fast. This is a substantial demonstration of Newton's third law. And here is a bigger scale one on which we could run a very quantitative experiment. So much water, so much heat energy put in, so much energy gotten in the angular velocity of the vehicle. And so, what must we now say? We have explored in the passing shows the first law in two parts, the second law, which is wrapped up in F equals ma, and the third law, referred to as action and reaction, which I will close in this way. Here is a very freewheeling vehicle, and you know that if I stand on it at rest and go forward, the cart must go backward, which it does. And I say that when I walk this way, the earth goes the other way. I thank you for your attention.